Insulation. Widely talked about. Continuous insulation, passive house. This is what we talk about. What insulations are there? How do we use them? Why do we use them? And what different sorts are there? Many, many different sorts. The one we're most familiar with, Fibreglass. Fibreglass is a product that's been around for many, many years. Has changed over the years. It's finer now. Isn't as brittle and as horrible as it used to be. It's still a process which can be quite harmful to the environment. It takes a lot of impact on the planet to produce this to a point, but it's very, very good. And over its lifetime, it will save a lot of energy. It can be used anywhere. This is a typical fiberglass. It can be used in floors, walls, ceilings. It can be put anywhere where there's a void. That's fiberglass. Now we have a new variant of that. We call it glass fibre. Glass fibre. It is a similar process, but this is 70% recycled glass. 70%. It's actually really, really good stuff. It forms individual fibres like a wool, but a fine wool. This would be put into any void, but we put it in with an air blowing machine. We'll talk about that later. But that is glass fibre, 70% recycled, much less of an impact on the planet, does exactly the same job. And it is available, this type of insulation is available in sheet form or on a roll, 70% recycled. Now that brings us to more carbon friendly, more friendly products to which we would consider earth products, what I term as an earth product, and that is natural fibres. So we're talking about timber, wood fibre. This literally is just wood fibre, and it's made into individual fibres, which is clubbed together, and this would be blown into any void, whether it's a floor, wall, or ceiling. Wood fibre can be used anywhere. Now, this is the basis for many other insulations to come. Another really good insulation and a recyclable fibre is cellulose. Cellulose is paper, recycled paper. Your newspapers, anything that goes can be recycled again to build a fibre which can be introduced to any void. Disadvantages is it is susceptible a little bit to damp potentially. But what these fibres do, all these fibres, glass fibre, wood fibre, cellulose, they all get filled in by a air blowing machine, a fibre master or whatever make fibre blowing machine. That means it gets pumped into any void. Now these products are very good to prevent slumping, because slumping is where over a period of time insulations can condense and drop within a void. So after 5 years, if you were to thermal image some of the builds that are out there today, you'll get voids around the tops of all the panels or the walls, which is basically allowing cold to transfer across. The insulation's not doing its job. But these insulations put into the correct pressure will not condense. They'll stay there for life, and they'll do their job consistently. That's why we use these fibres. Other earth products that we can use. We can use solid board. We can have structural boards. This again is a really good insulator, a wood product, a timber product. Underlaid for floors, underlaid for laminate, connection floorboards, another insulated board. A nice solid product. You can cut it to any size or shape you need, and it's an insulator, a natural product. Now the reason this is green is it's actually got a resistance to moisture. So this is why this is suitable for a floor. Very, very good. Another board, this can be cut and put in between your joists. This can be cut and put into your ceiling, your walls, or if you've got a suspended floor. Really good. Again, natural wood fibre, earth product. Then maybe a bit more familiar to us is something which we could replace fiberglass bats or fiberglass sheets in with stud work and various products like that. And that is, again, as a wood fibre, a little bit more coarse, but that is flexible, could be slightly compressed if needed, and it could be cut again to any side. Very little waste, very little impact. And that leads us to another one, very, very similar, but this is more condensed. This is a finer fibre which is condensed more and impacted very tightly. The reason is it's an external boarding. This would actually potentially go on the outside of a build, which is excellent for retrofit. So retrofit being an existing building to which we need to insulate and use our 5 basic principles to bring up to the biggest or the best value that we can get, the best thermal value. And that is this external insulation. It's actually got a membrane stuck to it on the outside, which means you can fix this directly to an outside wall. And that can be either counterbattened for airflow or even plastered directly onto. Okay. Excellent product. So when we come to insulations, there's many, many different types, many earth products out there to which we can use, as well as recycled materials. So retrofit, if this was to be on the external and you wanted to insulate to a window, you could use a combination of various products to achieve your thermal stability that you need within a build. If you were to take this to an edge of a window and return that, which is a structural board, into your window, you've then compensated for any cold bridge on the window. So there is a continuous insulation, maybe different types, but it's a continuous insulation without break. Anywhere we do not have a break of insulation, we do not have a cold bridge. Therefore, we have no heat loss to that point. And these can be used in various different ways. Same as if you've got an insulated floor. So this is your board. You've got a laminate floor over the top of that. And you've got an internal structural board going down onto that. And then you put your floor into there. Again, you've got a complete thermal break around your laminate floor. So wall, floor, combination of products which will achieve exactly what you need, which is thermability. So lots of natural products, lots of insulation out there, and we keep it as continuous as possible. That way we can cancel out any cold bridge. The other advantages to these boards and these natural fibres is, for instance, if you have a joist section where you have an existing building and a retrofit and you've got to go to a wall, these are a good thermal break, a natural product which is going to give you a natural break. You can even shorten joists within a wall and put an insulation on the end, or even box around a joist or whatever with these products and then re-brick into the wall. You know, there are many ways of retrofitting and new building where we can get a continuous insulation. It's using the right products in the correct places. And insulation.
John, can you just explain how it is that fiberglass is bad for the environment?
Fiberglass that we use at the moment, general waste, is still a good product. It saves energy. So therefore, in the long term, it's a good product. Anything that saves energy is. The issue we have with it is much of the fiberglasses today aren't recycled. They're actually produced from scratch. So therefore, fiberglass at the moment isn't necessarily the best way to go for the environment, even though it's a good insulator. It'll provide us with a good atmosphere to live in. and it will save money over time because you're not using the energy. It's the process before you use it which we're looking at, which is potentially a little bit more damaging to the environment because of the impact it has to produce it. How is fibre or wood fibre made? It is literally just wood fibred up. If you think about the process of paper, we use paper every single day in many, many ways in our life. Paper is a fibre product. Basically, it's a different form of doing that. So in other words, the fibres are probably extended and longer rather than condensed. The better the paper quality, because the fibre is very, very small. But if you improve on that and expand on it, you end up with paper or the raw timber or wood fibre that would make up that paper. Just slightly bigger fibres and they're put together in a slightly different way and not compressed. That way, it's 100% natural. It's just timber, pulp, which is dried out and then creates the fibres.
Excellent. You mentioned about slumping in existing homes that have been insulated with the cavity. What experience have you got of that, and how can that be dealt with and improved?
Slumping. Slumping is something which happens quite naturally within a void quite often, because if something's got vibration, don't necessarily have to move something to condense it. Just natural vibration. Us living every day, we make noise. We bang against walls. We move stuff about and condense and move things by creating vibration. That means that what happens is the fibres compress and it will compact and you end up with a void. So that's slumping, where it slumps down and it compresses. That can be avoided if it's thought about. Every void, regardless of size, shape, every void can be worked out to a square meterage. We take that square meterage and we work out how much needs to go in there and under what pressure to fill that void to avoid slump. So when we pump this into the wall with a fibre blowing machine, we can control the flow, we can control the pressure. So therefore, flow pressure equals an amount of a given amount of insulation for that void. If we achieve that, we should be avoiding the slump in the future.
So it's a little bit, it ties in with design and just calculating the design of the flow rate and the different factors. I just wanted you to touch on sort of solutions for example, a suspended timber floor. How might we consider approaching that, and what sort of things do we need to think about?
A floating timber floor, how do we insulate this? There's many different ways. Basically, it's a joist system. You've got a void underneath and you've got a floor on top. So there's a number of ways dealing with this. If you can take the floor off and expose the joists, we can airtight it, because we can lay an airtight membrane in between the joists at the correct depth. Then we can take our insulation and we can cut that in between the joists, and therefore suspending this on an airtight layer. And then when the floor goes down, then we've got an insulated floor area. We may not always be able to take the floor up, but there will usually be a void, in which case the airtightness will have to be taken care of underneath by spraying an airtight membrane, a liquid airtight membrane, and this being cut in between afterwards. Failing that, you may need to build up on top of the floor, in which case you'd use one of these products onto the floor, and then you would laminate or tile or whatever you need to do on top of that, on top of an existing floor, potentially with an airtight layer underneath. Because we've always got to think about air control or air tightness when it comes to insulations or any.
So we can go directly on top of the floor, we can lift the floor, and also we might have a crawl space, so maybe actually go underneath and work in that way. Just wanted you to touch a little bit on a really common floor type of people, and that is a concrete floor, and what sort of considerations you might have there.
When it comes to insulating an existing concrete floors on a retrofit, we need to have a look at what makeup we need to do that. Quite often a solid concrete floor means that it could actually be a potential cold bridge throughout the floor space, because it could be a raft type concrete floor. In which case, what do we need to do to compensate for that? Sometimes we're limited. The idea is that we may be able to raise, if we've got ceiling heights, may be able to raise the doorways, in which case we'll be able to take an insulation from the floor and we'll be able to completely insulate the floor with an airtightness around and underneath. Failing that, if we can't raise the doorways, we need to have a look to see how much build-up we can have, and we can take various steps. For example, we've already spoken about structural board. That's strong enough to walk on. We could put that down and then only allow an additional 9, 10, 12 mil on our floor. So that, combined with that, gives us insulated floor of only about 15 mil. So therefore we may be able to compensate that without raising doorways, but this would be a good insulator for taking the coldness away from the concrete, because we could potentially lose up to 30% of our heat through our floor. It acts like a fridge, if you like, that draws the heat out of the room. You can have a really warm room, but your feet will always be cold. That's because of the cold bridge on your concrete floor. And this will go to some part of compensating for that. But it does depend on your circumstances to which you have that you can adjust to. This is where it comes to flexibility. You can't always achieve what you want. Sometimes you have to compromise and just achieve the best you can with what you've got with a retrofit.
Excellent. So one of the challenges is with a concrete floor, literally sucking up the heat. So is it more common that we'll have a thermal break in concrete floors in more modern construction versus, back in the 1930s?
Yeah. Well, the older constructions, right through to when we first started using concrete floors, right up to 60s, 70s, the solid concrete base or raft was the way to go. It's the way they used to do it. So more modern floors, even concrete floors, tend to be better because insulations have been used for a long time now. Many concrete floors are actually suspended on T-beams and brick and block floors, which are suspended and have an airflow underneath and can be insulated on the top of the floating floor or concrete screed. So the older houses tend to be the ones that you have issues with when it comes to a concrete floor.
One of the challenges with retrofit is the amount of junctions that you might have in a house that doesn't have, shall we say, optimal form factor. How do you overcome those issues? Because you've got an existing build, you can't change the shape radically, but you're going to have some detailed work that needs to be done.
Retrofitting insulation. When you come to a retrofit, you've got existing connection points. If you're doing an external insulation, this by design will cancel out much of that because you're enveloping the whole form with an insulation anyway. So you're compensating for that. When you have to do an internal insulation, this is where you get potentially more problems and issues. Each individual problem has to be looked at as an individual solution. So we need to look at what product will compensate for that. if we have a joist in brickwork, there are some very good structural glasses out there, foam glass and various things like that. We can actually support the joists with an acro or something, suspend those joists, and we can break right in those joists and insulate around, even on the end of those, and then re-point them in. So that's potentially one way of dealing with a cold bridge or cold spot on a joist system. On the roof, we often have joists sitting in, on a roof where we have the roof joists and then we have the roof rafters. Those joists connecting into the wall or on a wall plate is a cold spot because it's a connection point, an existing connection. So if we're doing an internal insulation, we would again use the internal insulation and use potentially some form of insulating board on the ceiling and bring that up. And we could compensate for that to a point. Once again, you would be limited in your ceiling height to what you can do. But we can make a combination of different insulations to be able to compensate for those connection points. And the same on the floor. We've already on the floor, we can have two different types of insulation. So different earth products, different insulations, but we can use them to cancel out the same cold bridge areas just by using a combination of them.